So here's our simple code, and here's the assembly that's generated by this compilation. Now we want to walk through it in GDB, the GNU debugger, and just get a little bit of experience with seeing that interface, because you'll be using that throughout the rest of the class. Now, notionally, you're going to be using a GDB script, which we will name x.config, and this is just going to execute the following commands in GDB immediately after it starts up. So it's going to continuously display as hexadecimal the RA or return address register, the program counter, the S0 register, the stack pointer, the S0 again being the frame pointer, so frame pointer, stack pointer, A0, which is where the return value is placed by convention, by the ABI convention, A5, which is going to be used as a temporary register. Then it's going to display 6 giant words in GDB notation, or 6 64-bit values, starting at the stack pointer in hexadecimal, and it's going to continuously display 10 instructions starting at the program counter, and it'll set a breakpoint on main. So this is the notional script. In practice, I will have an x.config in your Docker container. I will update it if necessary, but probably this is going to be it for this first example. And then notionally, these are the commands we're going to do in the Docker container. Again, I'll update the website if anything about this changes, but it's basically just being in the home directory. So start out just logged into your Docker container. Then you're going to copy the JustReturn.c from the Git repository, which you will have checked out earlier in the class. You'll copy that into your home directory because essentially the path where it's compiled at is going to affect the overall layout of the stack. You compile it with GCC with the debugging symbols enabled and the optimization level 0, and then you'll just launch it with the quiet option, the X for execute commands in your xconfig, and the just return in your local directory. So let's go ahead and see that now. Okay, so now I'm in the QEMU RISC-V VM, and I will just go ahead and execute my compilation command, and then I will execute my GDB command to execute the program. So once GDB starts up in quiet mode, so no big output, it will have already executed all of the instructions in the x.config, and so all we have to do is go ahead and hit R to run the program, or you can type run. Okay, so then it starts out, it's got its continuous display of the registers, continuous display of part of the stack, and continuously displaying the next 10 assembly instructions. So here we have the initial value for the return address. This will return us back out of main to whichever function called main. Program counter is set to 5s and 6 to 8, and that is 5s and 6 to 8 right there, the first assembly instruction of main. The S0 or frame pointer is set to some address 7Fs AA8. You can see the stack pointer is set to 7Fs 920, so the frame pointer is somewhere up at a much higher address than the stack pointer. And we can see that, as is typical in debuggers, it will be displaying things in a low address is high, high address is low sort of fashion. So that's going to be opposite or upside down of what we see in our stack diagrams, but that's okay. Keeps you mentally flexible. So stack pointer starts out at 7Fs and 920, and you can see that there's some value already there, but again, we don't care about that value. That's something set by the function that runs before main. We're only going to care about the stack diagram for what is actually changed on the stack as a consequence of executing main. So then we have the A0, which we said is where the return value is going to be stored as the program is exiting. That's just the ABI convention, A0 and A1. If you have a 64-bit or less return value, it goes into A0. If you have a 128-bit value, it goes into A0 for the low bits and A1 for the high bits. And then A5 we're only displaying because it happens to be some temporary register that, due to unoptimized code, is being used to place values into the A0. Okay, so again, we really just want to see what's going on in the stack, so let's go ahead and look at our first assembly instruction and then execute it. So this is add I, and it's adding SP plus -16 because it's a signed 12-bit value behind the scenes. So SP minus 16 going back into SP. So if SP right now is 7Fs 920, then after this we will expect 7Fs 910 because 16 is hexadecimal 10 and 920 minus 10 is 910. So let's go ahead and do SI for step a single assembly instruction. Do that, and here's our update. Yes, indeed, the stack pointer is now set to 910, but you can see that there are values here on the stack. So we said that any value, any location that is at a lower address than the stack pointer should be treated as undefined. But now that we have moved the stack pointer down but not actually written anything there, it should be treated as uninitialized. So when you're drawing the stack diagrams yourself, just because you allocate stack space doesn't mean there's any significance to the values there yet. They're all just uninitialized values, and you should mark them as such. Until you see an actual store to that memory, these are just garbage values that you shouldn't give any mind to. But we do see a store coming up, store of a double word from the S0 register. So looking at S0, this was our 7Fs-AA8. S0 is our frame pointer. So we are going to be storing the frame pointer value to stack pointer plus 8 and treat that all as a memory address. So if our stack pointer right now points at 7Fs910, then 7Fs910 plus 8 is 7Fs918, and that would be this value right here. So this memory location is going to be overwritten by the value that is stored from S0 when we execute this instruction. So let's go ahead and hit SI. You can also just hit enter because the last command that was executed was SI. So I just hit enter and it does an SI again. So that does indeed lead to an overwriting of memory. So that was uninitialized value right here, uninitialized, not set by anyone, but now it is initialized. It's initialized to the value in S0. This value is still uninitialized, but you could confusingly think that that was the actual write of S0, but we saw that that was the same value before and after. It's just this value that actually changes before and after because that is the address that was being targeted, SP plus 8. So again, when you're drawing your stack diagrams, that's why you got to be very precise. You got to keep track of what's initialized and what's uninitialized. Okay, next assembly instruction. Add I again, so add the immediate 16, positive 16 now, to the stack pointer, but don't store it back into the stack pointer, store it back into S0, the frame pointer register. So now we are essentially moving the frame pointer. It used to point, or before this assembly instruction, it points at 7Fs-AA8, and now we are going to move it to point to stack pointer plus 16. So let's go ahead and do that. Executed that instruction, and now S0 is set to 7Fs and 920, which we actually remember was the stack pointer value at the beginning of this code before we subtracted 16 and moved it. So essentially the frame pointer is pointing where the stack pointer was pointing before we moved the stack pointer around. And that's essentially how frame pointers work in RISC-V code. We've got this 16 bytes, these two 8-byte values, two 64-bit values. This was the allocated space for main. This is essentially main's frame, and the frame pointer is being placed to a higher address just outside of main's frame. And it's saying, okay, well, right here is where the value was where the previous frame ends, and anything at a lower address will be associated with the new frame. Okay, so next assembly instruction, now we're doing the actual body of this, like all of this setup and all of the teardown, the function prologue, the function epilogue. These are all just sort of boilerplate that you get from default compilation. The actual thing done by JustReturn is just returning hex 41. So now we're going to do that. So we have an li for load immediate. Of course, the lie is a lie. It's actually add I, but load immediate 65 into A5. That's nice and easy to think about. So this A5 register is going to change to the value decimal 65 or hexadecimal 41. So 41 is what just returns, so that's going to be placed in that register. But it's only placed in that register temporarily because we next immediately see it moved from A5 into A0. So we step one more time and we see the A0 value updates to hex 41. And again, A0 is where the return values go when you're returning out of a function. Okay, and so now that it has successfully put the return value to 41, all it has to do is return back to the function that called it, deallocate its stack frame, and exit out of the function. So the last three instructions are a load, a dword, an add I, and a return. The load dword is going to take stack pointer plus 8, and we recall that the stack pointer plus 8 is the location where we stored the previous frame pointer. That's what S0 used to point at. We take the previous value of S0 and we just go ahead and load it from RAM, from the stack, back into S0. So execute that instruction, and we will see S0 is set back to the value it used to have, 7Fs-AA8. Then we add 16 to the stack pointer and store it back into the stack pointer. Thus, what the stack pointer is pointing at right now is 910, and plus 16 will bring it up to 920. So all of this will essentially be deallocated because it will become addresses that are less than the stack pointer, and therefore we will treat them as undefined. So step one more instruction. Yep, stack pointer went up to 920, and there's still that value sitting there on the stack that we don't know. It just came from whoever called it. And the final instruction is return. And we said that return is just a hard-coded compressed jump to register or jump to register, where the register is specifically set to the return address register. So it always shall be the return address register. That's just how that pseudo instruction works. So that means the program counter will be set to the value in the return address register. So we are returning back to the function that called main. So if we go ahead and step through that assembly instruction, here we find ourselves back into some function we don't know anything about, apparently called __libc_start_call_main, and we don't really, care about this. You just have to know the general idea that there's a function, that function calls into main, and when main is done, it returns back to the function. Now, if we wanted, we could do the disas for disassemble, and we could put in that address, and we could see, okay, this is the overall function, all sorts of assembly instructions, and we're right here. There had been a joller to A5. We knew about joller already because we said behind the scenes the ret is actually a compressed jump register, which is actually a jump register, which is actually a joller. So the joller A5 calls into main, and when main returns back, it finds itself back in this function at the next assembly instruction after that. But we don't really care about that. We just care at this point that we can actually step through assembly instructions in GDB, understand the code, see the effects that they have on the registers that they touch, and consequently understand things like stack diagrams, how the program is manipulating the stack, and so forth. So that was our first little taste of it, but you're going to be doing a lot of GDB debugging throughout the rest of this class as you learn new assembly instructions and see how different code is affecting the program state.